All right, good morning, everyone. I think we can go ahead and get started here. Thanks a lot for coming. Today, it's our pleasure to have Fabian Graus joining us from Munich. Fabian did his PhD at Kaiserslautern in Germany, where he worked with Michael Fleischhauer. He did a lot of seminal work already in his PhD. He won the DEMOP thesis prize of the German Physical Society, and he was a finalist of the thesis prize in the American Physical Society. He then went on to Harvard, spent many years there as a Moore postdoc fellow, working with a lot of folks there, including Eugene Demler. And then since then, he's gone back to Germany and back to Munich, where he's been now for several years. Fabian has made many contributions to the quantum simulation of fermionic systems, and particularly with the advent of quantum gas microscopes for fermions, Fabian has played kind of a large role in understanding microscopic ordering and strings and other snapshots of fermion systems, which is probably related to what he's going to tell us about today. So please join me in welcoming Fabian.
Yeah. Thanks so much. Thanks for the invitation. I hope the sound is good. So I want to basically give you an update, more or less, where quantum simulation of ultra-cold Fermi systems stands, why we are excited, and what we can do with them. The kind of topics we then care about is superconductivity. And in the end, I want to briefly give an outlook what, going beyond that, what we can do, maybe even addressing questions concerning lattice gauge theories. I want to start by thanking my collaborators. These are the key PhD students involved in the first row and the most senior folks, Annabelle, Eugene, Marcus, and Emmanuel on the experimental side, and their teams, of course, who all contributed to this. I thought, talking about quantum simulation, I should start off by giving a brief overview of what types of quantum simulation tools we have available these days. And the classic, I would say, is optical lattices, ultra-cold atoms in there. And then supplemented by the quantum gas microscopy tools, meaning that you can take pictures of the individual atoms, single site, single atom resolution. And what these systems are good for is basically to simulate Bose and Fermi Hubbard models, right? So you basically have hoppings and local interactions. I'll talk more about that in a bit, of course. There's always, been a wish to extend this to systems that have further range interactions, right? Say, if you take Coulomb electrons that you want to ultimately understand, they have further range Coulomb interactions. And one way to do this that's very, recently has lots of success is using Rydberg atoms. If you use Rydberg atoms, they have very, extended interactions. And they are now, the key tool, I would say, one of the key tools to realize spin models with further range interactions. So you trap your Rydberg atoms in tweezers, and then you can do a bunch of fantastic physics. Maybe this can also, pave the way for building a quantum computer someday. Now, naturally, you want to extend these two things, combine these two things, right? You want to combine hopping, a coherent motion of your particles, with some extended range interactions. And one way to do this, then basically allowing you to study extended Hubbard models, is using dipolar atoms or molecules. So the dipole interactions there can reach across a few lattice sites. And in this way, you can really combine the spin physics that is now, being explored in Rydberg platforms with the coherent lattice motion that you have in the Hubbard models. Of course, there's more platforms that I should mention here that all more or less realize spin models down here, superconducting qubits, trapped ions. Of course, once you are able to build a quantum computer that's scalable with them, you can also, again, address questions regarding tunneling and so on. But for now, they're mostly, I would say, they're mostly good at simulating spin physics. If you want Hubbard models, Bose Hubbard models in particular, photons are fantastic, and experiments have made them interact quite strongly. So there's a lot going on there. And one platform I should mention, and that's particularly exciting because you do have fermions, is quantum dots. So quantum dots ultimately realize actual electrons that interact strongly. And the cool thing about these systems, okay, they're hard to get to, large and fully coherent and disorder-free. But once you have them, they're cool because the way you can cool them down is by literally putting them in a fridge, right? You can reach extremely low temperatures down here. And that is actually a challenge for the other systems, right? In the other systems, we call them ultra-cold atoms, but actually the temperatures that they reach, and we'll get to that in a bit, they're, compared to the intrinsic energy scales, they're not as cold as we may wish. So that's certainly an advantage of these setups. All right, now let's say you have these quantum simulators. We should also talk about what are the contemporary targets. What do you want to do with them, right? And one goal that has been around since the advent of quantum simulation, probably, well, a bit later, probably, but since we started thinking seriously about ultra-cold atoms and optical lattices, one goal was to explore high TC superconductivity. That is the Fermi-Hubbard model, and really ask how much can the Fermi-Hubbard model tell us about high-temperature superconductors. So I'll talk about this in this talk a lot. Another interesting, thing we can do and try to do with quantum simulation is realize topological quantum matter. Here I want to mention this long, decades-old dream now to realize non-Abelian braiding in a many-body platform. And the reason quantum simulators are good for this is because they do offer coherent control of individual excitations, and that's what you need if you want to measure such type of braiding. Looking a bit further ahead, you can ask, what about lattice gauge theories, right? Things like the standard model, quantum chromodynamics, right? We would like to solve these models. They're very hard to solve in full generality, at least on classical computers. So if we could directly implement them with some sort of quantum simulator, that would be a fantastic thing to do. And finally, there's also quantum chemistry. I don't personally work much on that, but it's yet another fantastic application of quantum simulation platforms that I think has great potential in the future. All right, so this brings me to the outline of the talk. First, I want to talk about the plain vanilla Hubbard model and really ask the question, what can we learn about superconductivity, high TC superconductivity, and where do we stand in exploring this? Then I'll talk about pairing, and in the end, give a little outlook about lattice gauge theories. All right, so if we talk about high TC superconductivity, let's start by defining the problem. Where it all started is that BCS superconductivity was working and finally understood at some point. And it was clear that the TCs you reached are kind of limited to something around 30 Kelvin. So when, 1986, a superconductor was discovered in these copper oxides that has a TC above 30 Kelvin, there was great excitement. And over time, you can see it quickly, the TCs quickly started to rise. And that's what we call high TC superconductors now. Now, remarkably, only, 1 or 2 years, I would say, after the discovery of these high TC superconductors, the field more or less agreed that probably the physics has something to do with Hubbard or TJ type models, some type of lattice models. There's still some debate nowadays about the very details in these models, like is it really TJ or Hubbard? Is it some terms in there that the further range tunneling, how important are they, and so on and so forth. But the rough type of model was pretty clear early on. Now, let's talk about that model. In its simplest incarnation, this Hubbard model is defined on a square lattice. You have fermions tunneling around. They have spin. You have an SU2 spin symmetry, and you have a very strong dominant repulsive interaction on site. If they sit on the same side, and that's of course exactly what ultra-cold atoms in optical lattices are perfect in realizing. So these are the models they explore. Now, for the sake of understanding roughly the types of physics that's going on, it's very useful to break this down further to the TJ models. So there you assume very large U. That means there's no double occupancies. And then so these U terms here, these doublons here, they're basically prohibited from being there. And so then all that happens is you have spins on the lattice, maximum 1 spin per site. And there can be vacancies, so holes that basically tunnel around. And that's the type of competition you get there. Turns out there's an antiferromagnetic interaction between the spins. They favor a checkerboard pattern of the spins on the square lattice. And that's going to compete with the tunneling of these holes or these vacancies. And remarkably, the tunneling here is quite a bit bigger than the super exchange, this antiferromagnetic term. And this separation of energy scales, if you want to call it that, typically it's a factor of 3 between them. But that actually puts lots of frustration into the system, which makes it hard. In principle, there's the next nearest neighbor hopping terms. You can also directly include them in the basic model. And for the things I discuss, I will, they're not so important. I think they can make some quantitative differences that are important in the end, but for the, key physics, it doesn't matter. All right, now, basically this talk is about this paper that we wrote. It's kind of a review about where the cold atom exploration of these Fermi-Hubbard models stands. And it's also not a review because, the way it came about, we were invited to contribute to some, paper dedicated to Phil Anderson's. And so we said, what can we write? We said, oh, it would be great to have a review, but we also wanted to put in some new directions. And those are these, I'll talk about these mixed dimensional models in the end. You'll see it's a trick that gets the energy scales up. And that's also kind of in that paper. Now, what should I start with if not the phase diagram of ITC? So that's right now more or less the conjectured phase diagram of copper oxides, and that people think more or less matches the phase diagram of these plain vanilla 2D Hubbard models. Okay, and these stars and lines, that's where the cold atom exploration stands right now. So let's look at a few key features. Right, the x-axis is doping. That tells you how many holes you put into that system, how many of these vacancies that move around. This is temperature, and you can see we have these little cuts here. So this is the collective many-body physics at very low temperatures. Cold atoms, you can see there in this window here. Temperature in units of this antiferromagnetic coupling is between, let's say right now, 1/2 and 1 or 2. Okay, so all of these cold atom experiments, they're still fairly hot, exploring this intermediate temperature regime. And I want to now walk you through some of the key achievements there, and that also in passing explain the types of phases that you get there. It all started off with a 3D realization of pretty strong antiferromagnetic correlation in Randy Hewlett's group. That's in here. This diagram is basically the 2D version. That's what we expect in the plain 2D model that's most relevant for the cuprates. And the field also really got lots of motion when in 2017, Marcus Greiner in his group, they realized very extended antiferromagnetism in the system. This is the correlation length here as a function of temperature, and you can see as the temperature goes up, the correlation length goes up exponentially, reaching on the order of 8 lattices, and that's as big as that system was, right? So in that sense, antiferromagnetism down here has been reached. Another milestone at around the same time in one dimension was the realization of also antiferromagnetism. In that case, the holes move around, and if you just measure spin correlations, you get what's shown here on the left. And you can see with doping, the blue curve here, it doesn't look very antiferromagnetic. Antiferromagnetic would mean you get the tic-tac, positive, negative. But then if you basically take into account that every hole gives us a shift of this antiferromagnetic pattern, you can see this tic-tac pattern appear. So that's basically a way that antiferromagnetism is hidden in one dimension due to the motion of the holes. In 2D, this is more exciting, and I'll get to that in a bit. There's another experiment here by the group of Wasim Bakar. They went down in temperature here, but at finite doping. And what they did, it's a great example of what cold atoms can do. They basically prepared a state like this, some charge density wave. And you can see the lattice sites. This is individual lattice sites here. This is a very long distance modulation of a density. They let this go and looked at over time how it relaxed. And in looking precisely how this relaxed to an equilibrium state, they were able to extract the diffusion constant. And they combined this with the compressibility that they could measure independently. And then from this Nernst-Einstein equation got basically the resistivity. And what they found in this intermediate regime here is indeed a linear temperature resistivity, which is a hallmark of this strange metal that we get, around 20% doping. And that's also, something that's actively discussed in the solid state context. What's the origin of this linear T resistivity? So my work is also more on the side of what's happened next. In the group of Emanuel Bloch, we basically explored what happens if you put a single dopant and look at the structure of a single dopant. And this shows you very nicely what these quantum gas microscopes can do. Namely, you can look exactly at the type of spin correlations you expect around a single dopant. In this case, the dopant was the doublon. Doesn't really matter. Think of it as a hole. And they were up here, so fairly high temperatures still. But the temperatures were low enough in order to see an interesting effect, which is these bonds here, these diagonal bonds, they had negative antiferromagnetic correlations. And this is kind of remarkable because if you put a single hole in there and don't let it move, you would get a positive sign like in the background here, right? So in order to better understand this, you can actually resort to very simple pictures. And I want to show you the essential physics of what's going on here. You start with an antiferromagnet, you get this perfect checkerboard pattern, and then you create a hole. And that means you remove a spin, right? So you create a spin 1/2 excitation. Now what's going to happen is this hole is going to hop around. And as I said, the tunneling time scale is faster than this antiferromagnetic exchange. So basically, the hole will hop a few sites before it starts to feel the antiferromagnetism. However, it does feel it because, when the hole moves, it leaves behind these unhappy, frustrated bonds, right? And the energy of these configurations, that scales linear with distance, right? So the further the hole goes, the more energy it costs, even if every single step is, doesn't cost too much energy. And if we look at this picture, the rough, pictorial thinking you get is that, yes, well, there should be one spin excitation. This part here, if you look at that end of this string of frustrated bonds, this contains the information about what type of spin I removed, right? These are all upspins here. And yes, we initially removed the downspin, so that's correlated. If you just look around the hole here, on the other hand, you cannot tell whether you removed an upspin or a downspin, right? It really just depends on where you are. And in fact, you can make this more quantitative, but in the end, this string picture is able to explain these negative spin correlations observed around the mobile dopants. And namely, if you look at this this correlation here, this upspin here used to be there before the hole hopped right onto that side, right? So you can see this negative antifermionic correlation. That's precisely what they measured in that experiment, right? All right. Now, what we ask next is, this is for a single dopant, right? We want to understand what happens if you dope the system with a finite number of dopants. That's where the superconductivity is. And so then what we did is we basically looked together with Markus Kreiner's group at finite doping, and we cooked up an ensemble of individual string-like objects, right? And what we did theoretically first is we started taking the snapshots that they had at half filling without any dopants. And then we put in these string patterns by hand. We just randomly threw in holes, let them move around a little bit, mess up the pattern. And then we predicted that we analyzed the snapshots that we would get, looked at string patterns, looked at the number of them, and that's this green line. And then when we compared to the experimental data, we actually found that there's a great agreement with the number of such type of string patterns that we found. Okay, so this naive string picture that I initially told you about to get the key physics actually is able to explain quite a bit of this. Now, it's hard to see this shading, but around in this region here, at around 20%, you can see the number of string patterns kind of starts to saturate. And this is actually not surprising, because if we look at the types of string patterns we put in there, then you can see that they start to overlap, right? And once they overlap, there's a saturation. This makes sense, but this also tells you that around 20% doping, at the latest, there's a qualitative change of the picture, right? So we can probably not trust the string picture anymore over here, whereas at lower dopings, these string patterns don't overlap too much, right? So we think it's fairly reasonable to think of an ensemble of these individual string-like objects describing that regime. I should also say this comparison here that we do, this green line is completely free of any fit parameters, right? So the type of comparison we get here, we think it's pretty remarkable that we can predict finite doping properties like that. Right? Yep. Yeah. So what? Yeah. So what we did is we basically take the experimental data that we get at half filling at zero doping, right? And the individual data points is snapshots, right? Let's say it says here's an upspin, there's an downspin, and then we take any individual snapshot, and then we randomly put in holes. That means we remove spins, and then we remove these spins around in random directions, but with a probability distribution that we calculate from our theory, right? How likely is it to have a certain length of a string? And then that means we kind of mess up the antiferromagnetic pattern that they have initially in a certain way, but in a very controlled way. And of course, you can ask how sensitive is that just the result to the distribution of the length that you put in, right? So we have this sprinkled holes as comparison here. That's if you just put in those holes and don't move them around, right? So the fact that we deviate quite a lot from that, okay, that's not so surprising. They are, the strings have a finite length, but it tells you that yes, it's not pure coincidence. I mean, it's not any distribution would always agree, right? Yep. Yes. Right. Yes. 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 Absolutely right. So there's a few points that one can make. Is one is this is at finite temperature. So there's a certain thermal broadening of the string length distribution. And as you said, the average distribution in the ground state should be around 2-3 sites. Could be, yeah, right. So the tail goes to 6. With the thermal averaging, it's a bit longer. But that's enough to get these things to overlap quite substantially around 20% doping. But indeed, these are not huge objects. They're like a few lattice sites. Yeah. All right. So we also looked at other quantities like the spin correlations, right? Going back to this idea from before that around the dopants, they saw these diagonal correlations that change sign. And indeed, this is now just looking at this diagonal correlator, but not post-selected to where the holes are, right? If you just barely average over everything, don't just ignore the holes. And you can see these nearest neighbor, these diagonal correlations, they change sign. And again, this is around 20% doping, maybe a little bit before. But this basically shows us that somewhere around here, indeed, these ultra cold atom experiments also see a qualitative change of behavior, right? And in fact, here at low doping, we can again, explain the sign change and so on from just adding in these simple strings. And that is without letting the strings interact, which in reality would surely, eventually happen. All right, now we can look at this in even more detail, and this is again a project we had with Immanuel Bloch's group. They went to a little bit further dopings, slightly higher temperatures, and now they looked again at how these local spin correlations around the hole change with doping, right? So before I emphasize this blue diagonal bond here, and you can see if you dope, this is 50% doping now, this diagonal bond is always negative. Okay, so having this spin flip on that diagonal bond as compared to the bare antiferromagnet doesn't seem to be too surprising. But what they found is they looked at this straight bond here, and that ended up being positive on that side and turned into something negative if you went to higher doping, right? So they looked at this in more detail. This is this correlator, straight correlator right next to the dopant as a function of doping, and you can see this guy changes sign again around 20% doping. And so really around 20% doping, something seems to happen, and that's actually not new. If you look at the condensed matter type of perspective, this is it's very well known that around 20% doping you have the superconducting dome, but also that the nature of charge carriers changes dramatically. So this is here measurement of the Hall coefficient. So this tells you basically the carrier of charge, the density of charge carriers, right? And you can see it changes from being proportional to the whole doping P to something proportional to 1 plus P, around 20% doping. And this 1 plus P, that's what you expect if you just had free fermions in your Hubbard model, right? And this P, this is what you expect if you have the charge carriers be individual hole excitations inside of the antiferromagnet, right? And the nice thing is this type of change from free fermion-like to what I call this magnetic polaron-like behavior, this also is something that cold atoms at the fairly high temperatures that they're at can really map out, and they see this happening around 20% doping, right? And this basically gives us some confidence that this microscopic string-like descriptions that cold atoms could see signatures of at low doping actually works. So these systems are typically 10 by 10-ish. They can do a bit bigger now in the more modern experiments, but that's the order of magnitude. Yeah. And I should say at these high temperatures here, we don't think system size is a big limitation. Some of the experiments in Marcus Greiner's group, for example, and these ones too. So Marcus, these experiments here, they had a pretty flat trap. So we didn't have to worry about inhomogeneities, at least in this 10 by 10. These measurements here were done in a harmonic trap, but they can also switch it off now. So we'll have to see. I think that would be my main worry, the harmonic trap rather than the system size. Great. So another important property in solids that's known is that at low doping, we have a small Fermi surface. That's basically up to 20% doping. And that, again, matches what you expect from these magnetic polaron type structures. Whereas on the Fermi liquid side, beyond 20% doping, you get these large Fermi surfaces. So understanding that is of course, a key quest. It's the subject of debate. How can we understand this transition from this antiferromagnetic regime here to that large Fermi surface regime? And the way to go about it in solids, the way they observe that also is ARPIS, basically single electron spectroscopy. So then, of course, you can ask, can cold atoms do this too, right? And well, the answer is they kind of. So this is an experiment in Vasim Bakar's group. It's an ARPIS spectrum, but if you look at the energy resolution, so you can see the width here of this signal is, well, this is in units of tunneling. So, this is a pretty broad peak. Okay, so, I love this experiment, but I think there's still a lot of homework to do for the cold atoms to get better spectroscopic resolution of these type of quantities that, that are crucial to directly make contact with solids. Okay, now let me turn a little bit more to the story I want to tell you in the picture we developed, starting from the cold atoms. And so the perspective I want to take is that at low doping up to 20%, where this string picture applies, is that the charge carriers are these string-like objects. And as I already advertised, we can understand that as confined or bound states of a spinon and a charger. It's a spin and a charge excitation connected by a string. We're talking about short strings, three-ish lattices. And something I will mention later on is also that there could be other objects too that we find some numerical evidence for, which is charge on bound states. That's basically a pair of two holes connected by a similar type of string. But in those experiments, at least so far, there's no signatures of these whole strings. Temperature would certainly be a problem for that. All right. Now you can ask, how good is this picture of basically almost quark-like, particles that are confined with a string-like structure? And well, what we're really asking for is this picture of a linear confining potential true and good, right? And this is like as in quarks, right? If you take two quarks and you separate them further, you get a linear confining potential. So can we find some smoking evidence that that's the type of confining potential we have? To test this, we took some motivation from the physics of quarks, how people discovered quarks. And if you think about mesons are bound states of two quarks, right? Also believed to be connected with some sort of string in between them. And if you want to probe this directly this linear confining potential, what you should do is you just look at the types of excitations you can have. There are two sorts. You can have a vibrational excitation with a vibrational quantum number, being 2 instead of 1 in the ground state. Then you get these pions, for example, here. But there's another thing you can do, which is rotational excitations. You can take these quarks, rotate them around each other, and you get another elementary particle peak in your high energy experiments. And this way you can classify certain pion resonances, kaon resonances, and so on. That's how basically the quark picture can be quantified. And it turns out these rotational excitations of the quarks, they are very nice because they obey some nice relation between the angular momentum J that they have and the energy m squared here. So there's a linear relation between these. And okay, this formula here comes from some relativistic string model where you have a rotating string. We can't expect that in condensed matter, of course, right? But what we can ask is there a similar relation between something like the string tension here and the angular momentum, say, of our excitations. And can we see these other, long-lived excitations in the system? And the answer is basically yes. So we looked at the conventional ARPA spectrum that gives you the single hole spectral peak. That's this 1s excitation here. There's a little hump that we think is the first vibrational excitation, but you can see it's such a small hump. And this is kind of very challenging to do numerically, so you may not be too convinced. But once we put angular momentum into the system and create a hole that has angular momentum, going around its spin excitation, we can see a completely new peak appearing. And with different angular momentum, but it's basically here, and it's clearly above the ground state peak that we usually observe, right? And this means, beyond doubt, at least in the small TJ model, that there's a long-lived rotational excitation in the system that we can look at. And then, in fact, you can ask, how does the string tension here, the J over T, depend on or relate to the energy gap of that first peak? And it turns out these rotational states have linear relations here, whereas the vibrational peaks have this more curved form with this characteristic power law. Never mind the details, but the point is, by mapping out these dependencies, we can establish that, yes, there is such a linear confining potential, and this parton picture or this string picture is very good in the sense that it qualitatively predicts these type of features. And of course, that's another homework for quantum simulation, to go and do spectroscopy and directly probe these types of rotational excitation, which is something they, in principle, should be able to do by doing certain lattice modulations. All right, so I'll get back to these parton pictures in a bit, but first I want to wrap up this overview of the phase diagram. And of course, you should ask, what about these low temperature phases, right? The first question, this is the charge density wave here, or stripes, certainly shows up in lots of high TC cuprate compounds. And so you can ask, can we realize stripes in cold atoms? And well, we have to do some tricks, but we were able to do it. So the trick is we introduced a gradient along one direction of the lattice. And what this does, it's such a strong gradient that it completely switches off tunneling along that direction. But at the same time, this virtual super exchange antiferromagnetic coupling is still intact, right? So we get antiferromagnetism, which is 2D, but whole motion that's only 1D. And it turns out that unfrustrates the system quite a bit. And that means at the temperatures they're currently at, they can see stripes. And this is a G2 plot correlation of holes. And you can see if there's a hole in the middle, there's this reddish signal going up. That means it's quite likely to have more holes joining along this direction. It's blue in this direction. That means holes in the same chain would repel each other. And this indicates, this is a snapshot, right? There's a kind of a stripe-like thing of the holes that's forming, right? If you look a little bit at this signal, there's another red spot over here. Then that may actually be a sign of charge density wave patterns forming, right? There's a hole here, and then at a certain distance, there's another stripe of holes forming. At this point, though, the temperatures are too high, for us to conclusively say that they fully see these patterns. But these correlations, they're very, statistically significant. So we do know that the holes tend to bunch along these vertical lines. And then finally, the question is, what about superconductivity, right? And well, so far, we didn't see any D-wave superconductivity in the Fermi-Hubbard model. So that will be a quest for the future. But I want to devote the second part of the talk to discussing this a bit more. What can we learn about pairing from what I already told you about this microscopic understanding of the charge carriers? And experimentally, can we maybe even at least see some hole pairing in some simplified limits, which the answer will be yes. And I want to, in this case, tell you the result that I want to advertise, from the start. And it's, this is probably cold atom folks know this is a Feshbach resonance. And we love Feshbach resonances because what they allow you to get is tunable interactions, right? And in fact, this is not only for cold atoms. More recently, such type of resonant interactions have also been observed in certain semiconductors, including with photons, right? So we see these, this characteristic looks a bit like a voided level crossing shape here. And what I want to advertise is basically a picture that in these Hubbard models, in some form, we can have similar types of Feshbach resonances that on the one hand may help us understand the origin of pairing in high TC superconductors. And on the other hand, helps us to get a unified picture of some of, let's say, a broader class of condensed matter models. Okay, and the story I want to tell you before I talk about all this complicated 2D Hubbard physics, I want to start with a slightly different and a conceptually, I think, simpler variant, which is another type of superconductor. Basically, the story is it's a bilayer nickelate compound. People put pressure on it last year, and what they found is if you increase pressure, you basically get a structural phase transition of this material, and you get into a superconducting regime here. Okay, and the TC is something like 80 Kelvin, so clearly it's a quote-unquote new high-temperature superconductor, right? Now these nickelite oxides, they have a very similar structure to copper oxides, and people basically immediately proposed that the type of physics you should see is basically a bilayer Hubbard model. So in the simplest terms, think of just a bilayer copper oxide type of lattice, okay, with nickel replacing the copper. But the point is, these systems, and I'll explain why in a second, they are mixed dimensional in the sense that we don't expect there to be much tunneling between the two layers. But we do expect there to be super exchange. Okay, so it's exactly the type of trick that we played before in the cold atoms to get the stripes. That's the type of physics that seems to be at play here. And the funny thing is, before these new type of superconductors were discovered, these mixed systems is something we explored in cold atoms from a totally different perspective. We saw the first ever sign of direct hole pairing in a Hubbard type cold atom system. And the way we came to these models is by basically asking, what can we do to get very high pairing, basically binding energies, right? And that led us to exactly the same types of models, funny enough. So what are these models? How can we understand the physics? Well, basically, it's a bilayer model, a top layer, bottom layer. Both of them have two relevant orbitals. And there's lower lying DZ square orbitals down here. They're occupied by a single fermion. There's again a large Hubbard interaction that prevents more from being occupied. And the physics, we think, more or less takes place in these dx squared minus y squared orbitals. Those are exactly the orbitals that also play a role in the square lattice Hubbard type physics, right? And all the square lattice Hubbard physics goes into the plane, right? So you have one Hubbard type plane here and one Hubbard type plane here. Now, the point is, there's no tunneling. These orbitals don't overlap much. There shouldn't be much tunneling, but they couple to these lower lying energetically orbitals. And in here, you have a strong antiferromagnetic super exchange interaction. And what this can do is, even if these guys are kind of just sitting there, just watching, right, they can mediate an antiferromagnetic super exchange interaction between the physics layers. And that's exactly what you need to get a mixed D system, right? You get tunneling into the planes, but an antiferromagnetic super exchange between these two layers. And again, this is the trick that they played in cold atoms to realize this. They switch on a very large gradient that switches off the tunneling. They realize a metastable excited state in the sense that what you realize could decay to some low energy state, but they're so coherent that this decay just doesn't happen, right? So that's a different way of realizing this mixed dimensional property. So that's the type of system you should have in mind, right? And I'll discuss this now. What's the physics, right? Now, the reason this is interesting for pairing, you can very easily understand. Let's look at the limit when there's no tunneling between these within the layers, let's say, right? So this is the lower layer, the upper layer. Let's start with the case of half filling. At half filling, you just have singlets on the rungs, right? Singlets forming between the two layers. Now, if you put a single hole in, what you form is this, can think of it as one of these spin-on charge-on bound states. It's basically a hole, and you break up a singlet. And that costs an energy, to break up the singlet, J perp, this, interlayer super exchange, which is a nice energy scale. But then if you add a second hole, what you can do is you can just put it, remove this spin here. And that way you basically realize the second type of excitation, that now it's a charge-on excitation. It basically forgets all the information about spin. So it's a second type of meson if you want. And adding the second hole, you don't have to break up a singlet, right? So clearly this basically costs no energy, and therefore pairing is favored, right? So you get a binding energy of the two holes on the order of the super exchange energy. Okay, now you can ask, does this picture still hold if you go and switch on the tunneling in the plates? And that's actually a large energy scale. It can be larger than the super exchange. And here's the surprise. It turns out the binding energy, first it goes down below the super exchange. And I'll just use my mouse since the pointer ran out of battery. But here you can see you get binding energies at large tunneling that are even higher than just the energy it takes to break up the singlet. And it turns out this has to do again with the string pattern that forms when the holes move around, because they tilt these singlets, form a string of tilted singlets, and that actually gives rise to larger binding energies. This is a DMRG simulation on a ladder. It also works in a bilayer, at least in a small one that we can access numerically. And that's great news, right? That you can get binding energies that even exceed the super exchange interaction between the spins. Okay, now for the cold atoms, I told you they're so hot in relative energies, right? So this is obviously a good system to look for pairing, and that's exactly what they did. So they realized this mixed D system in a ladder, and then they measured the G2 correlations between the holes again. And you can see that if they use this mixed D setup on the blue data points, basically you can see there's clear bunching of holes next to each other, and that means there's binding of holes. Whereas if they use the standard 2D ladder, that's more frustrated, you can see there's anti-bunching and the holes would not bind at these energies. We estimate binding energies, they agree with numerics, so that's great. Okay, now the reason this is relevant to these new LNO high TC superconductors is that these systems are believed to be around 50% doping. So these physics orbitals, they should be 50% hole doped. That's quite a high doping. So it's not obvious that this simple string-like pictures that I developed at low doping that they should apply. And in this review that I mentioned, that's a review, but also has some things we thought were interesting. In it, we looked at this and we actually said, oh, probably there's some BC to BCS crossover. And it turns out these LNO superconductors, they should be somewhere here, close to this BC to BCS crossover. No? And we looked at this in more detail now, motivated, of course, by the discovery of these LNOs, and found that yes, indeed, these LNOs, they should be, if we estimate parameters, should be somewhere on the BCS side, close to the BC to BCS crossover. And this means, because you're close to the BC to BCS crossover, that you can have extremely high critical TCs for superconductivity. Okay, and if you estimate this, we find in this toy model 0.5 times J perp for the TC of the condensation. And if you translate this in numbers, this can be around 1000 Kelvin. Okay. Now, our model, of course, is too simple, which is why it's not 1000 Kelvin, that they actually measure. We're not worried about this. There are reasons this model is a bit too simplified, but it certainly motivates us, right, to see that there's a model we can understand some limit that can have TCs that are as high as, in typical units, around 1000 Kelvin. It's, of course, also extremely relevant for cold atoms because J half they can reach. So we thought, how can they measure, superconductivity in these systems? And we proposed to really realize exactly this type of bilayer using the mixed D trick, and actually play one more trick, which is to in one layer, let's say the bottom layer, to replace the holes by doublons. At first, it doesn't seem to do much, but it turns out what it gives you is if you measure density correlations in this doublon plus hole doped systems, that directly maps onto pairing correlations in your purely hole doped system by an exact mathematical mapping. Okay, and this is great because this means cold atoms are now in a position at the current temperatures they're at to directly measure phase coherence and then measure such type of a superconductor in the lab, right, without any further tricks they need to play. Okay, now this brings me to the end, which is, and I try to motivate you that these Cooper oxides, high TC superconductors, that we can learn something about where does pairing come from, right, and high TC. So the question is, all this story that I told you about now with the spin-on charge-ons and the charge-on charge-ons, can we somehow learn about this in the Cooper? So the way I want to think of them now is start with a Hubbard model or TJ model, right, and play a trick that Anderson has also played, and basically write it down in terms of partners. That is, we have spin and charge excitations. We first fractionalize them. But when Anderson did this for this celebrated resonating valence bond picture of high TC, what he proposed to do is basically think of a Fermi liquid of these fractionalized holes that completely forget and unbind from their spins, right? And okay, this RVB picture has some problems. But what I'm basically saying is, and I motivated this from the cold atom side previously, is that, well, what if what we have is actually bound states, mesonic states, okay? Then we can have different bound states. We can have spin on charge on bound states that I told you describe these single dopants quite well. We can have these charge on bound states. We saw them in the mixed Z case, right, to work well. Other combinations as well. In particular, we can also have another Cooper pair, right, which is a Cooper pair made up of two of these spin on charge-ons. So it's really, think of it as a Tetra-parton state, right? And so I want to start with this bound state picture and ask, what can happen now? And let's start with this mixed dimensional ladder that I advertised before. And in these ladders before, what I told you is that we directly form these charge on states where we have basically two holes on top of each other, right? But these guys are bosons, right? So it's much more interesting to go to the other limit when we have these spin-on charge-ons which know about the fermionic character of the charges, right? And one way to do that is to just add a repulsion between these holes and just tune that up to break them apart, right? So roughly speaking, what we would expect if we tune up this repulsion is that the ground state goes from being this charge-on state to just these free fermionic spin-on charge-on guys. So we did this in the simple toy model here and looked at the binding energies that we get at a repulsion which is 5 times J per up. That's definitely enough to break up these charge-on states, right? But nevertheless, we find as a function of doping binding energies that are sizable and positive. That means these holes still bind together. And this begs the question, why do they bind, right? We introduced a repulsion, a very strong repulsion, to break up these charge-on states. So where does this come from? And so let's look at this again and ask, well, if they bind, what type of physics do we get? And of course, coming with an AMO background, what you would expect is, that, well, this looks like you would have a bosonic superconductor here made up of a BC of these bosonic charge-on states, right? But if you then break them apart, if you have superconductivity on that side, that should be more BCS-like, right? You have the actual fermions that form the superconductor. And of course, this in AMO reminds you of, again, these Feshbach resonance that I advertised in the beginning, right? So in AMO physics, what you typically have is two atoms, AB. They can form a molecule, an AB molecule, right? And at some point, this molecule hits a scattering threshold and ceases to exist. And at that point, that's where the Feshbach resonance is. And the reason we like this is because if we are on this side, where the molecule exists, and we let these A and B scatter freely, right? We initialize them, scatter them on each other. The fact that there's a molecular state close by leads to a repulsive interaction on that side. But, and that's usually what we, like most if we want pairing, is that we can get an attractive interaction on the other side of the molecule, right? So we have free A and B particles, but there's an attraction, and this attraction can even diverge, right? You can get a divergent attractive interaction close to this resonance. And of course, you get where this is going. This is the exactly what's happening here. We're tuning this repulsion. We tune across that resonance, and what we expect is an attractive interaction, in this case, between these spin-on charge-on guys, right? So when we see this pairing energy dome here, what we think is what's happening is that we form a bound state, but it's a bound state of these spin-on charge-on guys. So it's really a Cooper pair made out of these other type of mesons, right? It's not the bosonic tightly bound pairs that condense, but it's really these fermions that form a more BCS-like superconductor. And of course, now we can take the next step and ask what could happen in the plain vanilla 2D Hubbard model, right? And the hypothesis we then formulated is that, well, if we have a close by bound state charge-on channel that's somewhat higher in energy, so if we're on the BCS side again of things, then we can have almost BCS-like superconductor of these individual spin-on charge-on-like fermions. Those are believed to describe the low doping regime of the cuprates. And if we have a D-wave charge-on state that kind of ceases to exist close by, then we can have a very strong D-wave type Feshbach resonance that in the end mediates an attractive pairing interaction between these spin-on charge-on guys. That's the hypothesis we formulated, and I don't have time to go into all the details why we think it could be true. But roughly speaking, what we did is we searched for this tightly bound charge-on channel, right? We have to, this is quite a strong statement to say that there's such a channel existing in these strongly correlated Hubbard models. What we started with is writing down an effective theory of strings, two holes connected by a string, tried to solve that and found some states. And then we compared it to numerics, right? So we calculated a pair spectrum And this is a simple comparison in a simplified TJZ model, but you can see, roughly speaking, the numerics finds there's a tightly bound pair state here, and we find similar structures in this effective theory, right? We did this comparison too for more realistic models, but roughly speaking, at low doping in these toy models, we do have a good understanding that these tightly bound whole pairs really exist. And that makes me excited about this prospect of having these resonances in there. And this basically brings me to the end of this part of the talk, and the rest is just an outlook. The summary is, maybe AMO physics and particle physics is not that different from correlated electrons. We know that in particle physics and AMO physics, all the rich structure comes from certain bound states that we can have, right? We have electrons and nucleons and so on. They can form bound states. The quarks too, they form bound states. And that gives rise to all this variety of rich physics we get. In correlated electrons, in many cases, it's fair to think of a pretty featureless Fermi liquid of some sort. But once we put in more types of bound states, like these Parton type bound states I advertised, we can expect more interesting features and ask, could this be a way to get tunable interactions? Can this be relevant for cuprates? Which brings us to also questions like how generic are the cuprates, right? Because the hypothesis I made is cuprates could be close to this resonance. Well, that's a strong statement, right? Because of course, if you fine-tune your model to something very special, then you can expect something special, right? But my argument is always a little bit, well, the cuprates are also very special, right? It's the material with the highest TC, right? So it's not just some material, it's a very special material. So, but this will be, questions that need to be answered. Is this a reasonable scenario to propose? Okay, so the last minute or so, just let me tell you something about lattice gauge theories. When we talk about lattice gauge theories, we're really switching gears now, right? I'm asking, can we use ultra-cold atoms to realize something completely different? A lattice gauge theory. What's special about a lattice gauge theory? Well, it's not just this plain vanilla Hubbard type model, but it's something that if you look around a lattice site and define a vertex or so, that has a conserved quantity. And so that means the type of model Hamiltonians that you want to implement to realize such models, they're very constrained, right? Instead of just hopping terms and local interactions, the types of interactions look a bit like this. So when the particles hop, they do something on the links in between. And you have to conserve these local quantities. Okay, so realizing this with ultra-cold atoms is a challenge because what we naturally have are these nearest neighbor spin models and our Hubbard type models, right? That's just what they have, right? So realizing these conserved quantities in terms like these is hard, right? So what can you do about this? Well, one way to do it is you just brute force design stuff, right? We followed this approach a little bit, cooked up a Floquet approach. You can shake a lattice, combine it with interaction in a smart way, and you get these type of weird looking, but gauge symmetry preserving hopping terms. So that's one way to go. The other way to go is to turn things around and say, well, let's just energetically protect our gauge symmetry first, right? Let's make sure that anything that deviates from this local conserved quantities costs energy, right? I call this top-down approach. You realize your interactions, for example, in Rydberg tweezer arrays, but it could be something else, and energetically enforce these constraints. And just to give you a rough idea, what I mean is you have local states and you separate them physical and unphysical states, right? And you want to make sure that your physics stays within those physical states. So the simplest thing you can do is you take your Hamiltonian and you just add an energy penalty for all the unphysical states, right? And you're done. And the problem typically is that this penalty is a weird many-body term, right? So we cannot simply add it. And then, but it turns out there's a few promising things, right? One is this is a Z2 lattice gauge theory. We found a two-body interaction that's natural in these Rydberg platforms or Hubbard models that allows you to isolate these physical states in the middle of your energy spectrum. And it turns out that's enough on any realistic timescale to protect any dynamics that you realize in that sector to stay within that sector. Okay, that's one way to approach it. And then this allows you to explore, things like these Franken-Schenker type phase diagram. That's a Z2 lattice gauge theory. We think we can supplement this with a U1 conservation of the number of matter particles. But the upshot is there's a lot of interesting models you can explore. You can look at how does confinement look like in these models. So this opens up the door for a bunch of things I'm happy to discuss after the talk. We looked at possible observables. And maybe as a kind of a last slide, right? This list is nice. These are local conserved quantities that are abelian, that could belong to an abelian group. The question is, how can we go to non-abelian theories? And at first, this may seem even more challenging, right? In fact, to give you an idea, what happens if you have a non-abelian basically means on each vertex now, you don't have just a conserved number, 1, 2, 3 or so, right? But you have a conserved spin. So it could be that there's a constraint that tells you that you always have to have a spin singlet within each of these little bubbles, okay? And it turns out in this particular case, again, these Hubbard models come in handy. Because if you write down the energy penalty for this having a local spin singlet now, you can break this up into a spin S.S part and a local spin. And it turns out these terms in the Hamiltonian, S.S spin interaction, that's exactly the antifermionic interaction we needed for the Hubbard type physics. And this S square interaction here, we can replace this by an attractive Hubbard interaction. And so the upshot is, non-Abelian sounds harder, but in this case, it's actually something that naturally appears in Hubbard-like models. And this is, I think, a good promise, for the future to use alkyl molecules or alkaline earth atoms to realize non-Abelian gauge theories too. Okay, so I think this is a great place to stop. I think I hope I showed you quantum simulation has a lot to explore. I focused on the phase diagram of Hubbard models. I think if if they get lower temperatures, there's also a chance to explore this very low temperature physics. But the other strategy we can always use is tune some parameters, get into regimes where the energy scales are even higher, and that's even better for if we want to design new materials that have even higher TCs, right? So it's actually fair to tune on things. Yes, and who knows? Maybe in a few 10 years or so, lattice gauge theories can also fully be explored. So thanks for your attention.
Fabian, for a great talk. Any other questions?
For both, right? I mean, I think the reason the experiments don't do different homeworks. Yes, yeah. I mean, the reason they didn't do it was because it's hard, but we also didn't propose anything simple. So it's really homework for both.
It's expensive imagine really
yeah, definitely. Yeah.
In that case, the size of the spin, which is close to
so I mean, yeah, that's true. I agree.
That's about a 30% of the
Yes. So I think first, of course, we looked at this numerics too. It's a bit different, right? Because they do pure ladder, right, with tunneling. So the physics with the tunneling is different from this mixed physics that we see. Yeah, just exchange between the legs and no tunneling. Yeah, microscopically, yes, that's true. But in the effective TJ model, then it's different, right? Because you have more symmetries. Yeah, right. But it's similar physics, right? I mean, but when we did do quantitative comparisons, right? Then of course it's different if we just switch off the tunneling but not a super exchange. So what we did also compare spin gap to the pairing gap, right? Or the binding energy, and we do find some differences, which is quite interesting. So we don't, and we also don't rely on identifying one with the other. I mean, I also when I started out said, experimentally. Well, I mean, in the numerics, we just do a spin excitation. Yeah, that's good. Experimentally, well, okay, measuring these gaps is kind of hard. So when I showed you the comparison of the binding energies, there we relied on an effective model that we fitted to the to the data to get the experimental binding energy. In principle, if they were able to measure energies, there's one proposal, for example, to take a ladder, split in two parts, and have a basically tunnel junction between them. And then measuring the oscillation frequency of pairs, you can directly measure a pairing gap. And I guess for a spin gap, you would do spin flip type spectroscopy. Then you could compare, separate them, distinguish them. No, so experiments have not directly measured these gaps, unfortunately. That would be cool to see. It's in principle doable, but not so easy, I'd say.
It's not a business.
Yeah. I mean, here we do see some differences, which we find interesting, right? To see that spin gap is not always the same as the pairing gap, and especially these string patterns, right? That's what. So for example, I showed the binding energies that exceed the super exchange energy, and this is only possible because of the strings that form. And that shows you, and that's not true for the spin gap. The spin gap is always J, or roughly, scales J.
Because it disappears as well.
Yeah, so in these systems here, it doesn't, right? So when I showed you the binding energy, that remains positive all the time. That's one of these quantitative details.
Other questions? All right, let's maybe stop here and